Okay, good afternoon, everybody. Today's topic for the class is graph coloring problem using backtracking. So again, we are talking about a problem where we'll create a state space tree and then we will traverse the tree using BFS or DFS. Okay, so first let's understand what the graph coloring problem is. So we are given a graph which has to be planar. We'll come to that in a while. We have to color the graph. Let's say a map. You have a map of countries. We want to color them in such a way that no two adjacent countries have the same color, so that it is you can visualize the map without getting confused about where the boundaries are. So we have to color. We consider the countries as vertices of the graph, and if it is an adjacent country, we mark it with we have an edge between those two. So just a second. So we have to assign colors to these vertices, which are our countries in this case, in such a way that no two adjacent vertices, they have the same color. So there is an optimization problem also for this graph coloring, where you have to determine the least number of colors you have to use to color such a graph. So if you have, let's say, this graph, how many colors at the most that you would need to color a graph would depend on the degree of the graph. So the maximum degree of the graph is 3 in this case. So at the most you need 4 colors for this particular case. So just a second. So this is a map. Okay. So if you see, let's say we are talking about this country here that I've marked with yellow. So if you see, there are 1, 2, 3, 4, 5, 6, 7, 8 adjacent countries to this particular country. So if we go by the degree method, the degree of this node is 8. So at the most you need 9 colors. But if you see, the 8 adjacent countries to this yellow country are, all of them are not adjacent to each other. So you can reuse the colors. So if you see, when I use blue here, then it's 2 adjacent countries are marked green, and then you are repeating red also twice, you are repeating green also once more, and then you have blue also once more. So first of all, we take this map coloring. It's also called the map coloring problem. We take the map, we convert the map into a graph like this. These are your vertices, and if they are adjacent to each other, then there is an edge between that. So now your map has been converted into a graph. Now the problem is of coloring the vertices of the graph in such a way that no two adjacent vertices have the same color. Adjacent would mean that there is an edge. If there is no edge, then there is no issue in coloring. Okay, so first let's come to the planar graph. So planar graph, if you can draw a graph in a plane in such a way that the edges don't cross each other, then we call that a planar graph. So graph coloring problem is applicable on planar graphs. So if this is a graph, or let's say a map, V1, V2, V3, V4, V5 are all vertices. So if you see, we can convert it into a graph where no two vertices, they cross each other. So then we can apply the graph coloring algorithm on this. So so how many colors we need? Generally, it is said that you need only 4 colors to color a planar graph. Okay, it was proposed in 1852, and It was proven using around 1400 graphs in a computer program in 1976. Okay. So, what is the four color theorem for map coloring? It states that any map can be colored with no more than four colors, so that no two countries with a common border share the same color. So, what you can do is a brute force approach would be you start with, let's say, country one, you color it, then color all the adjacent countries, and then move on so that there is no clash. Or you can say, I will, just like we find the subsets of a set, you can have all the possible combinations of how colors for all the possible vertices, and then whatever the results you get in the end, you can see which one fits your mm, criteria of no two adjacent vertices having the same color, and that will be your solution. So obviously that's not a good way to deal with this problem. So even when, let's say, we go about doing the coloring one, let's say one node at a time, then go to its adjacent vertices and then to their adjacent vertices, maybe somewhere you hit a clash, so you will have to retract back and then try some other color for the previous node. So first of all, if you have been given a map, convert it into a graph and have an adjacency matrix for the graph where you have a 1 if there is an edge or if they are adjacent, or a 0 if they are not adjacent. So this the least number of colors that are required to color any graph is known as the chromatic number of the graph. So the M coloring problem, it states that we have to find all the ways to color an undirected graph using at most m different colors so that no two adjacent vertices are of the same color. So for every value of m that is given to you, you will have a unique problem at hand. So you have to have a planar graph for it. So how do we go about it? So before I go into the coding part, let us have a look at this. So let's say we have this four nodes that you see here. This is your original graph, and you are given, you have three colors. It says red, blue, and yellow. It's not, it's actually red, maroon, and yellow in this case. So it's like this. At the beginning, for coloring the first node, this is your start point. For coloring the first node, if your m is equal to 3, that means three colors are available. You can use color number 1 or 2 or 3. That is what they have done: red, maroon, and yellow for the first node. Then the second node, you again have three colors available, but obviously one of the colors will clash with one. So you can have only 2 and 3 here. In this case, you can have 1 and 3. In this case, you can have 1 and 2. So your second, this is your level 1 is your first node, level 2 is your second node or the first adjacent node that you're looking into. You can color it in two ways. So you can see here, they're going to the second node and coloring it with the other two colors other than bright red. Similarly, you have maroon here, then red and yellow are the two options. You have yellow, you have maroon, and red as the two options. Okay, so this is your level 2. Now, when you move on to the third vertex, now again, since you are talking about the adjacent vertex of node number 2, again you have to, so when we talk of coloring here, this one and this one, it cannot be maroon because we are talking about the adjacent vertex of maroon. So again, only two color options left. And same in this, same the case with all the nodes in the next level. So you exclude the one that you're connected to. In this case, because the graph is like that, you're just adjacent to one node only, which has been colored. There is, so we started here, we colored it with whatever, then we colored this. Now this node is only connected to this node, which is already colored. So you just have to worry about this node. In case you had a edge like this, then you had to worry about this color X and this color Y before deciding what to color here. So you had to omit X and Y because both are adjacent. So in this case, the graph is simpler. So we don't have this. So we are fine with just worrying about the color of X. And based on that, we, okay, so let me just clear this a bit. So when you go to the next level, here, now we have to color the fourth node. So you have to check this fourth node is here adjacent to this node as well as this node. So you have to omit both these colors. So in this case, in this current case that we are looking into, both the colors are the same. So you can either use maroon or yellow. In this case, both the colors here, they are different. So you can only use maroon. So you just have one child for this here. So similarly, you will move ahead. If, let's say, suppose right now you are not seeing any place from where you are backtracking, that's because there are four nodes and there are three colors and the degree is only two. So it's quite comfortable coloring without having many clashes. So you see, you have a clash here. The only choice left is maroon. No, not the only choice left. You are coloring it maroon, and that's not a good option. So you can color it yellow here. So you have to, depending on the graph, this will happen. So let's just go here and try to use black color. If my graph was like this, just adding a little complication, I have three colors available. Okay, and I'll start coloring with color number one. This is 1, 2, and 3. So my first, so I take red, the first node I'm coloring. So the second node, when I color, I can color it with, I'll just take one branch for so that I can, we are taking now after red, the choices I have is blue and green. This is my red. So let's take now this here. Now the third one can only be colored by green because there are, blue is also adjacent and this red is also adjacent to this node. So this is your red, this is blue. You can just have green here. Okay, so moving ahead for the next, after this, just extend it like this. So what are the possible options other than red and green? I can have blue, so there's only one possible option in this case. So this will be blue, this will be blue, red, and so this is one way in which you can color. You'll have more solutions in the other branches. So let's just go to this branch as well. Here you have, this is already red, this is green. Now you can have what you can have here is blue, and again you cannot have, you'll have the diagonal. So all the solutions in this case will look like this. Let's say for some time that we have only two colors available, then we will not be able to do the coloring for this one. So that will not be enough. If you see the degree, in this case the maximum degree is 3, so at most you should have 3 colors. If, let's say, suppose I add an edge like this, then it will create a problem. So when I add an edge like this, till now it is fine. Now this last node has all the 3 as adjacent vertices. You will not be able to color it with red, green or blue. So this is like a no solution, so you have to backtrack and then try anything else which might do not have a solution in this case. So going back to the example, so how do we color the graph? You have a 2D matrix, your adjacency matrix, to store the graph. And how we this is the representation of your graph. So how do we store the color of the vertex? We store it in an array. So it's like this. Your x is an array. Let's say you have 5 vertices. This is your x. K is the number of vertices. So if you have m colors, let's say I have 4 colors, 1 2 3 4. So if the values are like this means vertex 1 is colored 1, 2 is colored 2, and 3 is colored 3, 4 is colored 4, 5 is colored 1. So this vertex, so what we need to know is we need to have a representation of the graph that we have done using adjacency matrix, and we need to have a a simple array to store the color of each node. And how will we decide the color of each node? By checking, we will go in order. So we'll start with m coloring 1. We start with k is equal to 1, and then we will assign it a color that we'll store here in this array. Then when we go on to color node number 2, then we will check if 1 is adjacent to 2. Based on that, we'll decide which color can be assigned to it. So the algo goes like this. You call m coloring 1. So k is the index of the next vertex to color. We start with 1. Then we have a loop where we get the next value of k. So what we do is we assign a legal value, would mean a legal color that you can assign to x1. Okay. This function will do the proper assignment. So the check whether there is an adjacent vertex with the same color, whether you can assign this color or not, that is done in this function. We'll get to this in a while. So it will tell us whether we can color or not. If it returns a 0, then that means there is no new color possible. We have exhausted all the colors, and because of the adjacent coloring, there is no color left to color this particular node. Otherwise, uh, since this is on repeat here, so if when we reach k is equal to n, that means all the colors vertices have been colored. This is like the exit from this repeat. Then we write down this array, which is actually the coloring scheme of the vertices. If not, then we call m coloring for the next node. Okay. So what does this next value do? The main work is done in next value, which tells you what is the value of the color to be assigned to a particular vertex. So let's go to next value. So what does next value do? So if, let's read it here. X1 to xk minus 1 have been assigned integer values in the range 1 to m such that the adjacent vertices have distinct integers. So that is the condition. So we are putting values of the color in x array, and if we have reached next value k, that means k minus 1 vertices have already been colored such that no adjacent vertices have the same color. Okay. A value of xk is determined in the range 0 to m. So the what your x can hold, this is x, m is from, let's say, 1 to 4. For example, we have 4 colors. The value 0 stands for no color assigned. So that is the condition. When if you return a 0, that means no color is assigned. Otherwise, if you return 1, 2, 3, 4, a color has been assigned. So xk is assigned the next highest numbered color while maintaining distinctness from the adjacent vertices of k. So what they do is, first you assign color 1, then you assign color 2 if it does not clash with the color of any adjacent vertex, then 3, then 4, and then if you cannot, it uses modular arithmetic to get back. So you see here, if you are at vertex number k, so that means k minus 1 vertices have already been colored, you will just increment the color. So if color number 2 was used for coloring the k matrix, you are using 3 now. Okay, and you're doing mod m plus 1 so that you are in this range of 1 to 4. And if the next color is 0, then that means all colors have been used and you have to return. So now, if something is assigned to this xk, we have to check that this is a distinct color. No adjacent vertices have the same color. So what do? You check this if condition. This one tells you whether there is an edge or not. If there is an edge, uh, it says g of kj is not equal to 0. That means it is equal to 1. So there is an edge. And if the color of the loop variable is j, if the previous colored node is k, and if there is an edge basically between k to j, then it checks if the color of k and color of j is distinct. If it is the same, then it has the same color. Then whatever you have assigned is not a proper color value, so you will break. And if you have actually checked this for all the, if this if condition here, just a second. So if this if condition here is true for all j values from 1 to n, that means for this color is good with all the adjacent vertices, then you have actually found the new color and you return. But if that is not the case, then it will keep on repeating. It will try the again, because okay, let me just erase. I just so this if here, it checks if there is an edge and if the color is same. If the color is same, then it will break. If the color is not same, then it will come out. So if it comes out because of break, then n will not be equal to n plus 1. Sorry, j will not be equal to n plus 1. It will be something before n. So that means you have to continue. If it is n plus 1, then that means you have checked all the adjacent vertices and your new color has been found. So if not, then you have to go back on this repeat, try the next color. Let's say if we had tried color 2 and it did not work with color 2 because of the adjacent vertices, then we'll go to color 3, color 4, as many are available, and then we'll do the same check. Okay, so is this clear? If you have any questions, just raise, or if you want me to repeat it, I'll do that before we move ahead. Okay, so let's get back here. So this is your next value. So this is your algo. You have to color k vertices with m values. You check the next value. If it is 0, you return. That means no color is possible. If not, then you write out the colors and you're done. Okay. Now, coming to the complexity of this algorithm. So if, for example, without if I had 3 colors and forget about checking adjacency, these are all the possible ways of coloring, right? So I'll have 3 options, so on. Okay. So for you have to check at every level. This tree is without doing any color check. This is like all the possible ways of coloring, even with clashes and all. Okay. So how many internal nodes in the state space tree? It says it is this sum. What is this sum? It is 1 plus m square, so on, mn. Right? So if there are m colors, this is the, let's say m is 3. So you have 3 nodes at level 1. So worst case, the next level will have 3 square, that is 9 nodes. And this, when we go down, this will be 3 cube. So 27 nodes and so on. So this is excluding that clash one, because obviously one of the colors here and one of the colors here is going to clash. So it's obviously less than that. So when you sum it up, what you get is m to the power n is the highest this, and you have to check at each node. You have to check the color clash with all the adjacent nodes in the next value to determine the legal coloring. So this m into n is the additional factor. So overall it will be O. O means it is less than that, which we can figure out because when we are considering this tree, we are considering all the 3 children in case m is equal to. So you can see if you go back to next value function, so you see that you roughly, based on how we calculate the time, you see that for every node, if you have n nodes, sorry, how many nodes we have? We have k nodes. So we are checking for j varies from 1 to n. So this is uh, for n number of nodes. You are checking. This is basically a for loop of size n. Okay, roughly. And then if you go back to if you go back to your main, you're calling next value k. Okay, it has a for loop which is n, and you have to do this for every. So next value will be called for all the, basically all the internal nodes, and we calculated that to be around m to the power n. So that's why it is O of m to the power n. Okay, so just, so just like we did, if we had two colors available for this graph, which we did in the beginning, we would not be able to color three colors we can solve. So this is the same graph. Okay, so just give me a second. Just wanted to, okay, I think, yeah, I had another old slide. I'm not able to find that. So for now, I think that is it. I'll look for some more notes on this. Uh, so this is your backtracking problem. So I was thinking about what to do after your NP completeness and NP hard. That is just theoretical. So we'll just go over it briefly. Uh, there was something we did not cover in data structures, which I think is important for you, which we will do here. Uh, I had told you we'll talk about B trees. We didn't do B trees, right? In data structures. So B trees and AVL trees, and the rotations in trees, that is quite useful in other subjects as well. B trees has a lot of application. So we will do them. We'll not do the programming part, but we'll just go over them and study the basic concepts of binary, this B trees, and maybe avial trees also, and there is a similar concept of red black trees. So I want to do those towards the end, because we have almost completed. Backtracking, this is all we generally cover. We just have NP completeness, that is just like half a lecture, that there's not much in that. You'll read more about that in your, have you done a theory of computation, or you have it next semester? Next semester. So you'll do a lot more of that in your next semester course. So for now, that will be our last lecture, and then we'll do study a bit about trees in the end. Maybe two, three more lectures, and you're done. And one assignment which I'll give you for those 10 marks. Okay, so Aman, please take the attendance.
Yes, ma'am. Done, ma'am.
Yeah, just done. Okay, fine. So,
Yes, ma'am.
okay, that's it. So let's end the class here. Enjoy your lunch.